Okay, guys, for the next 4 days, for the next 4 days, we've got to stay focused because we have shorter class periods, so we don't have any wiggle room. What I mean by that is we don't have any wiggle room to kind of mess around. So, let's focus. And if I feel like you're not doing a good job focusing, what I'll end up just doing is saying, hey, you didn't get through everything, but you're going to have to read about it. Okay? Believe it or not, that happens far more often than you'll ever admit when you get to college. It happens a lot in college where the teacher, even if you weren't wasting time in class, he gets to the end of class period and he hasn't covered a couple things, he'll say, you need to read on this topic. Does that make sense? You'll have to do that. That's a reality. Yes, Shane? Right over here. Okay, so what we're going to talk about today is momentum, probably a word you have heard before, experienced before. Let me see. Hold on, don't put this in. Yeah, don't put this in. It says, Newton noticed that moving objects have a property. That determines how much force is required to change their motion. When you think of momentum, what comes to mind? What did you say? You were starting to get onto something that would be good.
Something goes fast,
So if they're going fast, usually we say that they have a lot of momentum. And if we say it's slow, we say it doesn't have a lot of momentum. And you're going to find out that our momentum equation has velocity in it. Should make sense. Okay? The other part of the momentum equation that's very important is the mass. Okay, because it says, I don't know why I pulled out a spoon to point. There's a spoon in my pocket. Okay? So it's saying, notice that objects that are moving have a property that determines how much force is required to change them. And didn't we talk about how bigger objects resist a change in motion more than littler objects do?
Yeah.
Okay? What was that whole concept? What was there it is, inertia. Okay? So not only does the speed play in how much momentum it has, but mass plays a fact, or an important, it's really important to the concept of momentum. So, let's tackle this. Here's your equation, and yes, you're probably thinking, that's a goofy symbol that they use for momentum. Back in your book. Our last new variable for this chapter is momentum. Its symbol is P. It's actually the Greek symbol rho, but I just use P. Because the Greek symbol rho looks like a P. And this actually has a unit that could have been derived, but they didn't. What is the most common mass unit? What's the most common velocity unit? They do not have a derived unit for this, so the most common unit for momentum is actually a kilogram times a meter per second. Yeah. Normally I write out like meter per second, but I'm not going to write out a kilogram times a meter per second because that'll get really long. So go ahead and put this in the back of your notes after you have gotten the stuff in the front. Quick review here. What does direct mean?
Oh, same.
Same. Both go up, both go down. What is inverse?
Opposite.
Opposites. One goes up, the other goes down. Yes?
Unit, does that say kilograms times?
Yep, kilogram times a meter per second. I'm probably not going to ask you a question on that. Okay, it's a vector quantity. Yep, right. This is a vector quantity in here, and it should make sense because it's got what in it? Velocity. Yeah. Which means we will have to give a direction if they give us a direction. Way to ask that, Carly. Good job. Mass is scalar. Okay? All right. Go ahead and put this in, and this should make. You've kind of already alluded to a lot of this. What's that? Yeah, you have to write that. Okay, the key thing up here is this has to be true for us to make this connection. It says if objects are moving at the same speed, the heavier object has more momentum. Why does the speed have to be the same? What was that?
One has more speed than the other, but obviously it has more.
Okay, yeah. So this is a two-variable equation here. Pay attention here, because believe it or not, you can have an object that has less mass, that has more momentum than an object that has more mass. Let me prove it to you. Okay, let's use this equation just to prove this. Let's say I have an object that is 100 kilograms, and it's moving at 1 meter per second. Its momentum is 100. Does that make sense? Okay? Now, let's say that I have a 20 kilogram object, but it's moving at 10 meters per second. Its momentum is 200. Okay? So it is possible that you have a lighter object that could have more momentum than a heavier object, but in order for that to be true, it's got to be moving a lot faster. So it is a two-variable equation. So if I'm going to say this statement, heavier means more momentum, I can only say that they're at the same speed. Because I just showed you an example where heavier doesn't give you more momentum. I just showed you it, didn't I? For example, if you've got a really massive object that's not moving at all, does it have any momentum? No. Okay? So it's important that most of the time heavier means more momentum. But I could have a ping pong ball have more momentum than a bowling ball if I shoot the ping pong ball really fast. Does that make sense? Okay. All right, now we're holding what constant? Same what? Same mass. Again, we are going to compare that most of the time the faster object has more momentum. But remember, it's dependent upon your velocity as well. Or your mass as well, excuse me. So the only way to say faster means more momentum is if they have the same mass. So if I have two bowling balls, one traveling faster than the other, which one has more momentum? The one going faster. Because the bowling balls are the same mass. If I have a bowling ball and a tennis ball, okay? The tennis ball is moving faster. Can you prove to me that the tennis ball has more momentum? No, because they have what? They have, well, I heard it, different masses. Okay? So the only way to know for sure that an object is more momentum if it's going faster is if they have the same mass. Okay? Really important. Same mass. If they have the same mass, you know the faster one has momentum, because we know that sometimes we can have a faster object that actually has less momentum if the mass is different. And I proved it to you. Here's some vocab words. I gave you vocab sheet at the beginning of this chapter, correct?
Yeah.
Okay, I just want to make sure. This should be fairly straightforward. Okay, what does linear mean in math? Abby? Straight. So when you're doing linear equations, you're graphing a straight line is what you're doing. Now you probably don't deal with rotating stuff very much in math class yet. Rotating stuff, there's an angle involved. That's why we call it angular momentum. Is it possible to have linear momentum and angular momentum at the same time? Give me an example. Yeah. Everybody hear what he said?
Yeah.
He said when you're bowling, it's still going, it still has a linear portion of it, but it's also rotating at the same time. Okay, so you can have both, and you would actually, it would be pretty difficult to do the physics behind something that has both linear and angular momentum. Okay, we don't even do that in high school physics, like senior level. Okay, that'd be more a college level, maybe even, possibly even graduate level. Okay, straight line, linear, turning or rotating is called angular. The reason why turning or rotating is called angular is when you're not going in a straight line, you have an angle. All right. Law of conservation of momentum. Woo! A lot of times when we deal with momentum, it's many times dealing with the collision. And what this law is saying is, when two objects collide, their individual momentums might change, but the sum of their momentum is the same. What do I mean by that?
One ball hitting another ball that's not moving, and a lot of the momentum from the first ball moving goes to the other ball.
So the momentum gets just transferred, is what you're saying. Think of it like you're playing pool. Okay? And one ball's not moving, another ball you shoot at the ball that's not moving. Okay, this doesn't always happen, but usually the ball that hits the stop ball either comes to a stop or after it hits it's slowly rolling a little bit, and the ball that was at rest is now what? Moving and accelerating pretty quickly. Okay, so what happened was, yes, the individual ball's momentum changed, but the sum of the two balls' momentum is the same because the momentum just got transferred from one object to the other. Does that make sense? And this is true about any situation. Okay? Following? Does that make sense from a logical? You've experienced it, you've probably seen that before. Yeah? Guys, it's warm in here. You guys are looking extra sleepy today. You're looking sleepy. You're looking a little, you got your hand on your head. I mean, you two are looking sleepy. What's the matter? You all right? Long weekend? It's a Monday. Iowa assessments. Huh? Fair enough. Just to warn you, the Iowa assessments are really bad at science. What I mean by that is you're going to be getting science stuff that doesn't deal with this stuff probably. It's really dumb how Iowa assessments do it. They actually give you stuff
They
like,
don't give you stuff you learn in school.
no.
That's, yeah, like there's all that's not in that we have to.
What is it?
It's usually either stuff you learned years ago or stuff that you won't learn until next year. It's really dumb. So,
I was the only one.
anyway, alright, so momentum is conserved due to collisions. Hold on. Okay, yeah, put this in. This is important to note, like I said, that momentum gets transferred from one object to the other, it just doesn't go bye-bye. Two objects collide, momentum just doesn't disappear, it just gets transferred from one object to another. As soon as we get this in, I'm going to move on since I've kind of already talked about that. You can get up and do some jumping jacks.
No, we don't have any wiggle room.
Illegal.
I said legal?
Yeah. No. Hey, she told me.
No, it's just the way it's like wiggle.
I think that's Mari is in your way.
Yeah. But I got it now.
Got it? Everybody?
Yeah. Johnny, jump and read it to you. No, I got it.
What? Got it now, Rose? Okay. So we got big object, little object.
What is it? Animation. What are
Okay.
you doing?
So during a collision, it does look. Do both of their speeds change?
Yeah.
Yes. They're both of their speed changes, but their speed changes are changed in such that their momentum is going to be conserved. One just gets transferred to the other. Happen a lot. This is grand football.
No, it looks. No,
Hold on. Let me see if I want you to put this in. Oh, yep. Put this in. This is just saying what I said. Again, I'm not going to elaborate on this. I've already talked about it, but I do want it in your notes. What? Oh, because I said it?
Yeah.
This is very similar to another variable we haven't talked about yet. What is another thing that gets transferred from one object to another? Energy. We'll talk about that next chapter. What? Kinetic and potential?
Yeah.
Next chapter.
It's like yelling at a pencil.
It has no kinetic energy.
Making a point.
I'm not.
Believe it or not, the particles that make up that ruler do have kinetic energy. Alright, got it?
Yeah.
Okay. Do not put this in, but I do want to talk about it. It says impulse is, and we do this in physics, I'm not going to make you put this in. So what causes an object to change momentum is a force over a time period. Okay? What I thought was always cool when I actually first taught this in physics was like, oh, this makes so much sense about trampolines. When you jump on a trampoline, does it hurt?
No.
When you jump off the trampoline onto the ground, does it hurt? Yes.
Not really.
I mean,
Depends how high you are in the air.
yeah, it's like if you just like, I'm talking about you jump up off the trampoline
Oh, yeah, that-
and then to the ground. I'm not talking just falling to the ground.
Crunch.
Okay, and here's why, guys. In both cases, your change of momentum is the same. Either it changes your momentum and sends you back up, or it changes your momentum and causes you to stop when you hit the ground. The change of momentum when you jump off the trampoline versus on the trampoline is exactly the same. The reason why one hurts and one doesn't is when you jump on the ground, your change of momentum is pretty much in a split second. So if the change of momentum is the same, and this is really small, what do you think the force is? Big. That's why it hurts when you jump onto the ground. But when you are on a trampoline, do you stop immediately? No, it's like over a time period that it slowly stops you. That make sense? So the time period goes up, and does what to the force need to stop you? And so that's why when you jump on a trampoline, it doesn't hurt, because it doesn't take as much force to stop you if it does it over time. That's why firefighters will use safety nets or whatever, or trampoline-like objects when people are jumping out of buildings. We don't want them to jump and just hit the ground. That wouldn't feel good, would it? No. Okay. Is that it? Is that the time?
That is time.
Oh my goodness. All right. Stop. Who said that? Before you quickly go, again, here's your equation. Here's your equation. Now listen.
No.
I'm giving you a worksheet. There's math in here. But listen. Do you know what the most common unit for mass is?
Yes, those are.
Everyone following? Hey, stop. Listen. Do you know what the most common unit for velocity is? I just gave you momentum's units. So, just like any problem, label your variables. Okay, label your variables, plug them in to the equation, and you'll find you're either multiplying or dividing. That's all you're doing. Okay? But if you don't get this right, will you get that right? No, you will not. So, here's your homework. I'll get you guys to walk out.
And now it's time for lunch.
Hey.
No, it's not.
Proud of you.
Liars.
Sounds out dirty?
Yes,
Nope, did anybody touch it?
I did.
He didn't. Nobody.
The way in that little animation where the two football players, their hands are like
I've got dirty right now. I've got a dirty foot.
Thank you.
He wasn't diving for the ball, I know that.
Alright, she decided to be the quarterback. She doesn't even know if the test is.
He fell.
Whatever, I swear
He
to God.
didn't bring him with him.
John, you doing? You got on mine?
Stop clicking your tongue.
No.
Oh!
He fell.
I was sitting up there for like half of the time you were sitting there because I had bad time.
Don't need to. I want to get
So,
you.
tell me to come back in. I'm
How
not.
you said you didn't have the number of
I said I did not do it.
Oh, okay. So I need to get you, Johnny, I need to get you your,
Wait, Shane. So she told me not to come back, like she didn't say anything about being on second. So I
So
assumed.
go around the corner. She said she'll come over and
No, she didn't say that. She didn't say that I should come in once I'm done. She did.